Homework 3.4, the rational zero theorem. Zeros of polynomial functions, video 8. Homework due Wednesday, May 27th, 2020 at 11:59 p.m. I'm not really going to put a list of homework questions on here for this one, but if I had to, it would be 15, 16, and 17, which will be the next video. But before we wrap up this series of videos and the skills I'm going to hold you responsible for, I'd like to just point out a few theorems. I know that we have one theorem in the name of this section, the rational zero theorem, but there are some other theorems that we have used and we're about to use that deserve some mention. So nothing to work here, just some things to explain. The first theorem is called the fundamental theorem of algebra. This was actually discovered by a mathematician named Carl Gauss when he was 22. It was part of his doctoral thesis. I forget exactly when. I want to say it was in the 1800s. May have been sooner. Actually, I've got that answer right here. Where is it? Well, I thought I did. 1799. So it was almost the 1800s. But the fundamental theorem of algebra basically says this. If f of x is a polynomial function of degree n greater than or equal to 1, then f of x has at least one complex zero. So there's at least one complex number that will make it equal to 0. Now, as a consequence of that, and I'm not going to prove it, the function has n complex zeros if you count repeats. If you saw the previous video, -1 was a 0 twice, and then there were 2 complex zeros for a total of 4, and it was a 4th degree polynomial. So basically all this says is the highest power equals the most number of zeros. Because if you don't count repeats, like the previous example, there were only 3 zeros, -1, 2 plus 9i, and 2 minus 9i. So there were only 3 zeros even though it was a 4th degree polynomial because the -1 was counted twice. So if you count repeated ones, it will match the degree. If you don't, then the degree is the most number of zeros you can have. The complex roots theorem, I kind of mentioned this when we were discussing Descartes' rule of signs about why you subtract an even number from the count when you're doing sign change counts. But the complex roots theorem says if f of x is a polynomial with real coefficients, meaning that none of the numbers in front can have i's, which technically they can, but not for this theorem. So if you have a polynomial function with real coefficients and x equals a plus bi is a 0, in other words, putting this complex number in makes it equal to 0, then x equals a minus bi is also a 0. So in other words, complex solutions occur in pairs. These are called conjugates. We didn't define that in the first video because we didn't talk about complex division, but any two complex numbers that are the same except for the sign in the middle, so a plus bi and a minus bi, are called complex conjugates. Conjugates. I know in foreign language classes, conjugate is a verb. Here it's a noun, conjugate. And all the complex roots theorem says is a polynomial function with real coefficients, complex roots occur in conjugate pairs. So in the last example, 2 plus 9i was a 0, 2 minus 9i was a 0. It's a direct consequence of the plus minus in the quadratic formula, although that's not how you prove it. And then the last one is the linear factorization theorem, which we've sort of seen already, that says if a function is a polynomial function of degree n greater than or equal to 1, and by the way, the reason this is here is if the degree is 0, that means there are no x's and it's a constant function like f of x equals 5. So this is just saying that you actually have some x's in your function. Then f of x equals some number times x minus c1 times x minus c2 all the way through x minus cn, where c1, c2, all the way through cn are your zeros. In other words, every 0 builds a factor. We've seen that already in the factor theorem. All this is saying is that you can always write a function as some number times the product of all the factors where each factor is x minus a 0. Now the zeros may be real and they may be complex, and they may not be unique. So if 0 shows up more than once, then its factor would show up more than once. So what are we going to do in the last video? And what's up with the last 3 homework questions, 15, 16, and 17? We kind of already did it when we were discovering the rational zero theorem, but the last questions are, let's reverse the process. I'm going to tell you some information about the zeros. I want you to go build the function. And we've already seen it. A 0 becomes a factor. The factors get stuck together and multiplied. Now what's up with this constant in front? And I should have mentioned that this a represents some constant like 5 or -3. Well, we'll see what that's about in a moment. It has to do with something called an initial condition. So for the last video, which will pertain to the last 3 questions of the homework, we're going to put everything back together.